Welcome to the Deep Dive, where we take your curiosity, our sources, and embark on a fascinating journey. Today, we're plunging into the cosmic dance of cataclysmic variables. It's
Yeah,
a bit of a mouthful, but trust us, these are some of the most dynamic and puzzling objects in our universe.
they really are. And what's fascinating here is how these, well, seemingly small binary star systems hold keys to understanding much larger phenomena, things like black holes, even active galactic nuclei.
Wow.
At their core, cataclysmic variables, or CVs we often call them, they're compact interacting binaries. Basically, a white dwarf star is actively pulling material from a companion star.
Like a cosmic vampire.
Kind of, yeah, constantly feeding.
Okay, let's break this down a bit for you. We're
Yeah.
talking about a white dwarf that's the super dense, leftover core of a star,
Mm.
basically eating from another nearby star. And
Mhm.
here's where it gets really interesting. Depending on the white dwarf's magnetic field, this whole eating process changes dramatically.
That's right.
If it's non-magnetic, the material sort of swirls into a disk around the white dwarf, like water down a drain.
Pretty much, yeah, an accretion disk.
Mm.
But if the magnetic field is strong enough, it can cut that disk short.
Truncate it.
Exactly. Or even completely suppress it, just get rid of it altogether. It guides the material directly down onto the white dwarf's magnetic poles.
And that's how we get these different types. Intermediate polars or polar.
Indeed, intermediate polars, they have these partially truncated disks and magnetic fields, pretty strong ones, around maybe 100 to 1,000 Tesla.
Okay.
But polars, their fields are huge, exceeding 1,000 Tesla. I mean, thousands of times stronger than Earth's field.
Wow.
And that completely suppresses the disk. The material just flows straight down the field lines. So our mission today is to dive deep into how new, incredibly precise data from the Gaia mission is completely transforming our understanding of these, well, mysterious systems.
Right. Solving some long-standing puzzles.
And, as always seems to happen in astronomy, revealing new ones too.
Absolutely. So for years, astronomers have had this nagging feeling about cataclysmic variables. There just weren't enough of them.
Right.
Theoretical models kept predicting far more than we were actually spotting out there. It was like some kind of cosmic disappearing act.
That's a really critical point, the space density of CVs, essentially. How many of them are packed into a certain volume of space. That's a crucial constraint for our models of how they form and evolve.
Makes sense.
Early studies, binary population synthesis studies, like back in the 90s from DeCool and Politano, they suggested we should find, well, quite a lot, maybe 200 to 2,000 per cubic megaparsec. Sorry, that should be zero point 0.2 to 2.0 by 10 euro per cubic parsec.
Okay, quite a range, but a lot.
Yeah. More recent models, Gaia and Nelson in 2015, Bologna and colleagues in 2018, they refined these estimates down. More like 1 to 2 by 10 euro per cubic parsec. So fewer, but still a significant number.
But here's where the observation started to throw a real curveball, wasn't it?
Yeah.
These predicted values were consistently much higher than what astronomers were actually observing.
Yeah.
It wasn't just a small discrepancy. It suggested something pretty fundamental was, well, off in our cosmic calculations.
Precisely. And historically, getting accurate space densities was incredibly hard. Our X-ray observations were limited, you see, and we lacked precise parallax distances.
Parallax being that tiny shift we see.
Yeah, the shift in a star's apparent position as Earth orbits the sun. It's key for measuring distance. Without accurate distances, it's hard to know their true spatial distribution.
Enter the Gaia mission, the incredible European Space Observatory that's just meticulously mapping our galaxy.
Gaia has been a game changer.
So with Gaia Data Release 2 back in 2018, things really started to change, didn't they?
They really did. At that time, our best X-ray samples were actually quite small. For instance, the ROSAT Bright survey, that was an X-ray mission in the 90s, it only had about 15 non-magnetic CVs listed.
Only 15.
Yeah. And SwiftBat, which detects gamma ray bursts but also sees X-rays, it gave us a similar number of intermediate polars. So, not huge numbers to work with. Then Andreas Schwope in 2018 used the new Gaia DR2 distances, and these were accurate to better than 5% for many objects to reevaluate these limited samples.
And the big aha moment. What did we find the missing ones?
Well, not exactly find them, but the big realization was that many of the previous distances, especially for the intermediate polars, had been significantly underestimated. They were further away than we thought.
Ah, okay. So they weren't necessarily rarer, just farther.
In part, yes. So Schwope provided revised upper limits for their space densities, which counterintuitively were even lower than previous estimates, less than 1.1 by 10-year-old per cubic parsec for non-magnetic CVs, for instance.
So the gap between theory and observation actually got wider?
It deepened the discrepancy, yeah. But now, crucially, it was based on much more accurate data. We knew the observation side was more solid.
Okay.
And we also have larger X-ray samples coming online now, thanks to Erossata, the all-sky survey that ran from 2019 to 2022. It's about 25 times more sensitive than Rossat, so we expect a lot more data from that soon.
Right, so more pieces of the puzzle are coming. But while those big surveys were gearing up, there was another crucial study, Pala et al., in 2020. They took a different tack.
Yes, they did. It was a really interesting approach. They created what's called a volume-limited sample. They look specifically within 150 parsecs, that's about 490 light years, so relatively nearby cosmically speaking.
Okay, our local neighborhood.
Exactly. Using Gaia DR2 parallaxes, they identified 42 objects in that volume and estimated their sample was about 80% complete. They even discovered 2 new CVs themselves using the Gaia data.
Wow. And what did they find within that local sample?
One of the key findings, and this was quite striking, was a very high fraction of magnetic cataclysmic variables, 36%.
36%. That seems high. Especially, didn't you say earlier that we don't see many magnetic white dwarfs before they become CVs? In the sort of pre-CV stage?
That's absolutely right. There's a noticeable absence of strongly magnetic white dwarfs in the detached binary systems that are thought to be the progenitors, the ancestors of CVs.
So where do the magnetic fields come from? Or how did they become so common?
That's a major question. It highlights that the evolution of these magnetic systems must be, explicitly included in the next generation of population models. We can't just treat them as an afterthought.
Got it. So their calculated space density, did it match the theories?
Well, they calculated a space density of 4.87, 0.7 by 10.7 per cubic parsec, which is a bit higher than Schwope's upper limits, but still significantly lower than what the theoretical models predict.
Still missing most of them then?
Still missing potentially hundreds for everyone we see. The discrepancy remained even with this careful, volume-limited approach.
So what does this all mean for, like, the nitty-gritty, the inner workings of these systems? Can these new observations tell us about how the white dwarf is actually feeding and how the whole system evolves over time?
They absolutely can. It's one of the exciting things Gaia enables. See, the mass accretion process heats the white dwarf. So its effective temperature, how hot it is, gives us a direct clue about its average accretion rate over long timescales. Ah, okay. Hotter means more eating.
Generally, yes. And the Pala et al. Study provided some really detailed insights here. For example, they confirmed that long-period CVs, those with orbital periods longer than about 3 hours, have mean accretion rates about 10 times higher than short-period systems.
10 times higher? Why the difference?
It's down to how the systems lose angular momentum, which is what drives the stars closer and fuels the accretion. In long-period systems, you have magnetic wind breaking, like stellar wind, carrying away momentum and gravitational wave radiation both working. In short-period systems, magnetic braking becomes much less efficient, so it's mainly just gravitational waves, which are slower.
Okay, so hotter white dwarfs in those long-period systems. That tells us something about their evolutionary stage, right?
Exactly. It confirms that part of the standard model. But then there's the white dwarf itself. Is it changing?
Right. Like, is it gaining mass significance?
That's the question. Pala et al. Looked at the masses for 14 white dwarfs in their 150 parsec sample where masses were available. The average mass they found was 0.83 ponenal 0.17 solar masses. 0.83. Wait, isn't the typical mass for a single white dwarf much lower, like 0.6 solar masses?
Precisely. And it's also higher than the white dwarfs in those detached progenitor systems.
So they are gaining mass, or something else is selecting for initially heavier white dwarfs.
Well, it strongly suggests that the accretion process is increasing their mass over time. And this finding, that they end up heavier, it supports the idea that we might need additional mechanisms for angular momentum loss beyond just the standard magnetic braking and gravitational waves.
More efficient ways to bring the stars together.
Something like that, yeah. To explain both the inferred higher accretion rates needed to heat them and the larger final masses we observe.
Okay, we've talked accretion, we've talked mass.
Yeah.
But what about the overall life cycle? The sources mention some really fascinating, almost like counterintuitive stages. The period gap, the period minimum, and the period bounce. Can you unpack those? They sound a bit like a cosmic game of leapfrog.
Haha. Yeah, they are quite peculiar stages. If we step back, the big picture is that CV evolution is mainly governed by two things: the loss of orbital angular momentum, which we've discussed,
Right, pulling in closer.
and the internal structure of the donor star, the one losing mass. Now, the donor star is losing mass pretty fast, often on a timescale similar to its thermal timescale, the time it takes to adjust its internal temperature structure.
So it can't quite keep up.
Exactly. It gets driven slightly out of thermal equilibrium. It ends up being a bit hotter and more bloated, puffier than an isolated star of the same mass would be.
Okay.
And this deviation from equilibrium is thought to be the key driver behind the period gap and the period minimum.
So as angular momentum is lost, the stars get closer, the orbital period gets shorter.
Yeah.
That makes sense.
Precisely. They generally evolve from long periods down to short periods. Now, for long periods, say above about 3 hours, you have both magnetic braking and gravitational waves driving the evolution. But around 3 hours, something important happens inside the donor star. It becomes fully convective. Its whole interior starts churning like boiling water.
Okay, and that affects things how?
Well, the standard model suggests that this full convection changes the star's magnetic field structure dramatically. It seems to make magnetic wind braking much, much less efficient.
It puts the brakes on the braking.
You could say that, yeah.
Yeah.
So, with the main driving force weakened, the donor star actually shrinks a little bit, just enough to detach from its Roche lobe, that gravitational boundary we mentioned. Accretion temporarily stops, or at least drastically reduces.
And that's our period gap, this pause in feeding.
That's the period gap, yes. It's thought to be this range between about 2 and 3 hours where the system evolves essentially as a detached binary. It's still losing angular momentum, but now only through the much slower process of gravitational wave radiation.
Okay, so it drifts across this gap.
Exactly. Until, at around 2 hours, the orbit has shrunk enough due to gravitational waves that the donor star fills its Roche lobe again.
And the feeding resumes.
Accretion resumes, yes. And below the gap, the CV continues to evolve towards shorter and shorter periods, still driven mainly by gravitational waves, until it reaches what we call the period minimum, around 80 minutes or so.
The shortest possible orbit.
Pretty much. At this point, the mass loss timescale becomes much, much shorter than the donor star's thermal timescale. It's losing mass so incredibly fast now.
Even faster than before.
Relative to its ability to adjust, yes, it gets driven way out of thermal equilibrium. And crucially, it stops shrinking in response to mass loss. It can't contract any further.
And then, wait, it gets really weird here.
Right.
It evolves back to longer periods, becoming a period bouncer. That seems completely backwards.
It does, doesn't it? But because the donor star can no longer shrink as it loses mass, further mass loss actually forces the orbit to start expanding again to conserve angular momentum, so the period starts to increase. These are the period bouncers.
Mind blown slightly.
Oh.
Okay, so what did the Pallas study find about these bouncers? Are they common?
Well, that's where another puzzle comes in. Theory predicts a significant fraction of CVs should be in this period bounce phase, but Palla et al. Found a very low fraction in their nearby sample, only about 7%.
Only 7%. What theory predicts? Yeah.
An order of magnitude more, yeah. So finding so few period bouncers is actually one of the major open problems in understanding CV evolution. It's another big discrepancy.
Wow. Okay, so Gaia DR2 and the Pallas study really shook things up. It sounds like Gaia's just been a total game changer. What are the most recent findings? Has Gaia DR3, the later data release, shed more light?
Yes, absolutely. A more recent study by Kanbei and colleagues in 2023 utilized an even larger sample. They gathered 1,587 CVs.
Whoa, that's way more.
A lot more, yeah. Many came from the AAVSO database. That's the American Association of Variable Star Observers, a fantastic citizen science project, by the way.
Cool.
And they combined this larger list with the improved distances from Gaia DR3, so even better data.
And what did they find? Did they finally solve the missing CV problem?
Well, they crunched the numbers and derived updated local space densities. They got 6.89 is 1.2 by 10 per cubic parsec for all CDs, and 2.1 IO, 0.5 by 10 for the magnetic system specifically.
So, slightly higher than Palla et al., but still.
Still broadly confirming the previous estimates, yeah, and still showing a significant discrepancy with the population synthesis models. The mystery persists.
So the missing CVs are still missing, but maybe we have a slightly better count of how many are missing. What's the latest thinking then? Where are they? Are the models just fundamentally wrong?
That's the million-dollar question, isn't it? Kanbei et al. Suggests that the ongoing discrepancy likely arises from CVs that are just intrinsically very difficult to detect.
Like what?
particularly systems with very, very low mass loss rates. These would be incredibly faint, and also potentially a large population of systems that are currently dormant in the period gap.
The ones taking a break.
Exactly. They're not accreting much, so they're not bright in X-rays or optical light, making them hard to spot in typical surveys.
So they could be out there, just hidden.
That's one strong possibility. The Kenbei study also derives something called the exponential scale height that tells you how concentrated the systems are towards the plane of the Milky Way.
Okay.
And they found scale heights that were considerably larger, meaning more spread out vertically, than previous studies suggested, about 375 parsecs for all CVs, 281 for the magnetic ones. That helps us understand their overall distribution in the galaxy better, but it doesn't solve the missing number problem directly.
Okay, let's try and unpack this then. Looking back at our deep dive today, I mean, from totally redefining distances to uncovering these like missing evolutionary stages like the period bouncers, and even hinting at maybe needing new physics for angular momentum loss, Gaia has truly thrown a massive spotlight on cataclysmic variables.
It really has.
It's clearly not just about counting stars anymore, is it? It's
Yeah.
about understanding the fundamental processes, the real physics governing how these binary stars live and die across the cosmos.
Exactly. And, the application of Gaia data to understanding CVs is, believe it or not, still at a relatively early stage. There's so much more to dig into.
Really?
Oh, yeah. And these persistent discrepancies we've talked about between the observations and the population synthesis models, they're actually a good thing in a way.
How so?
Because they're catalyzing incredible new research. They're forcing theorists to refine the models of stellar and binary evolution, and they're pushing observers to develop new strategies, new surveys, to actually find this large population of systems in our own solar neighborhood that apparently still remain undetected.
It just goes to show, doesn't it, how much more there is to learn out there. And maybe this is a thought for you, the listener.
Yeah.
What other surprising, currently undetected cosmic phenomena might still be hiding in plain sight, just waiting for the next generation of amazing tools like Gaia was for CVs to finally reveal them?
It's a thought that truly inspires further exploration, definitely. Makes you wonder what's next.